everyone, and welcome to Jam Academy. In this example, my primary objective is to help you know how to calculate the kinetic energy of an extended body. Now, in the previous example, we did deal with a single particle system in which the mass was concentrated at a single point, in which case the kinetic energy was just equal to half mv squared. But the situation is different when the mass is extended. So the question says a thin uniform rod, the word uniform is important here, a thin uniform bar of mass m and length l rotates with a constant angular velocity omega about a pivot at one end. The question is to derive an expression for the kinetic energy of this bar. Derive an expression for the kinetic energy of this bar. Now, since we are dealing with an extended body, to make matters simple, my recommendation is that always begin by choosing a small segment of the body. Let's choose our small segment. Let the mass of this small segment, we call this a small increment, is dm, and the length of the segment is dl. Let's also assume that the distance of this segment from the pivot is L. Now, that being said, we know that the bar is uniform. That means that the linear density is constant. The linear density lambda is just the total mass divided by the total length, and that is equal to dm all divided by dx. The beauty of that equation is that dm is gonna be equal to m all divided by L multiplied by dx. So this equation right here gives us a means to calculate the mass of our little infinitesimal increment. Now, the next thing that you will like to keep in mind is the object rotates with a constant angular velocity omega. The object rotates with a constant angular velocity omega. Now, there is a relationship between the linear velocity of the bar and the angular velocity of the bar. We know that v is equal to r omega. So for this incremental mass, v x will be equal to that radius x multiplied by omega, where omega is simply equal to 2 pi all divided by t, where t is the period of rotation of the bar. So this is equal to 2 pi x all divided by t. Now, the next thing you need to bear in mind is that the kinetic energy of the bar is simply going to be equal to the integral of 1/2 dm v squared. 1/2 dm v squared. Another way to put this is I'm going to take out the 1/2, the integral of v squared dm. I prefer to put it that way. Now, we know what dm is and we know what v squared is, so all we have to do is substitute the variable. So this is going to be 1/2 the integral of v squared, which is just 2 pi all divided by tx, all of this squared multiplied by dm, and dm is capital M over L dx. We can remember that we are integrating this function with respect to x. So an x is the length of the bar. So we are integrating from 0 to L. We're integrating from 0 to L. We're integrating from 0 to capital M right there. So you should take note of the limits of integration. So the next thing that we would like to do is to simplify that particular expression. So K will be equal to, let's take all the constants out, 2 pi over t all squared will be 4 pi squared over t. So we will have here 2 pi squared multiplied by m all divided by t squared multiplied by L. We're integrating from 0 to L. This is x squared dx. Now you must pay attention to the various terms, not to neglect any. So this will be equal to 2 pi squared m all divided by t squared L x cubed all divided by 3 from 0 to L, which will be equal to 2 pi squared multiplied by m all divided by t squared L cubed divided by 3. So you can simplify this to give us k equal to 2 over 3 m pi squared all divided by t squared L squared. Now this is the expression for the kinetic energy of the object. This will give us the expression for the kinetic energy of the object. Now please, if you have any questions regarding this problem, I will sincerely ask you to ask your question in the discussion forum below this video, and we will be able to help you. Thank you so much for your time, and remain blessed. Bye.